Hello, this is Ms. Fleet, and today we are going to cover the second half of Chapter 16. We covered the first half of Chapter 16, actually the majority of it, before we left for spring break when we talked about nucleophilic substitution reactions. And so today we're going to move on to something called elimination reactions and also the common uses of halogen alkanes that you should know. Alright, so our learning objectives. There's 3 of them. The first one is to recall the chemistry of halogen alkanes as exemplified by the elimination of hydrogen bromide from 2-bromopropane. This is a specific reaction. If you'll recall, in an elimination reaction, you are eliminating a molecule from an alkane or a halogen alkane. So an elimination reaction looks like this. And I'll do this exact reaction right here. Let's say we had 2-bromopropane. Propane means 3 carbons long. 2-bromo means the bromine is on carbon 2. So I'm writing it in displayed. Pardon my handwriting, as always. And so we need to eliminate a small molecule. So we would be eliminating HBr, hydrogen bromide. So that means we're taking the bromine away and we're taking a neighboring hydrogen away, one that's right next door. So it doesn't matter because this is a symmetrical molecule, which hydrogen I take as long as it's either on the carbon over here or the carbon over there. So I could take this away. And so I would end up with running out of space, but I would run and one more hydrogen, I would end up with this. Notice the HBr would be produced as a second product, and because you don't have the H and you don't have the Br anymore, you have to create a double bond. So if you'll recall, in an elimination reaction, you always go from a single bond to a double bond between 2 carbons. That is something that always happens in elimination. And the second learning objective is to explain the use of fluoroalkanes and halogen fluoroalkanes in terms of their chemical inertness, meaning that they are unreactive. And finally, to recognize the concern of the effect of CFCs, chlorofluoroalkanes, in the ozone layer. So let's go ahead and get started. Just like before, what I'm going to do is you're going to have some questions to go over. I'm going to have you answer the questions and then we are going to review them. So here's the first question. Halogen alkanes undergo a range of nucleophilic substitution reactions. Which reaction proceeds only by SN1? So go ahead, pause the video. You'll get a chance to look over this and answer the question. Alright, so let's see if we remember SN1. In an SN1 mechanism, what type of halogen alkane was necessary? It was a tertiary, which we also put a little 3 for tertiary, halogen alkane. And so in which of these examples is there a tertiary halogen alkane? Well, if you got the answer right, you got that it was D. If you look at D and you expand it, CH3, 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 this is a tertiary halogen alkane because the carbon that has the halogen, this one, has 3 carbons directly connected to it, which means that it forms a carbocation quite easily in comparison to the rest. Now, notice the word only. The reason why that is important is because in C, technically, this could have happened with an SN1 or an SN2 reaction when you have a secondary halogen alkane. But because this was a tertiary halogen alkane, it will only favor the SN1 mechanisms. Good job if you remembered. Let's take a look at bell work number 2. And yes, I do have several today. Bell work 2. Halogen alkanes react with sodium hydroxide aqueous. That is going to become important later today in today's lesson, either by an SN1 mechanism or by an SN2 mechanism. The mechanism followed by the reaction depends on the structure of the halogen alkane. This question is about the reaction of 3-bromo-3-ethyl pentane. And so then they give you the molecule, which you should try to see just to make sure you know how to expand it. But even by this name, you can pretty much figure out if it's SN1 or SN2. And then it asks which statement is correct. So once again, I'm going to give you a moment to see if you got it right, and then we'll check. All right, so let's take a look. First, I'm going to go ahead and draw it out. 3-bromo-3-ethyl pentane. So pentane is 5 carbons in a row. And on the third, we have an ethane, which we know is a CH2CH3. And we have a bromine. And then if you'll notice, if you filled in the hydrogens, you would have this is CH3, this is CH2, this is none, this is CH2, and this is CH3. Notice that this is a CH2CH3, this is a CH2CH3, this is a CH2CH3, so you could group it all together into the structural form, which is, exactly what that looks like. And so once you've drawn out and expanded this molecule, it should be relatively easy to see at least part of the answer. Because this is a tertiary halogen alkane, we know that the mechanism has to be SN1, so we can take out the answer options C and D. Now, what is the intermediate for the mechanism? If you'll recall, when the bromine leaves, it takes its electrons with it, so it becomes Br-, which means that this is a carbocation. And so the answer is stabilization of the intermediate cation by 3 alkyl groups. If you got that, pat yourself on the back. And we'll move on. There's actually a Bellwork 3 because I just couldn't resist. All right, this is the third one. So take a look over it. This one is interesting because you have a activation energy diagram, and you've probably never seen one like this before. But just to take a look at it here, you've got 1 energy of activation, and you've got 2 energies of activation if you read it left to right, the progress of reaction, meaning that this must be a 2-step reaction. So with that little clue, plus the fact they told you it was tertiary, which of these answers do you believe are correct? I'll give you a moment to try to figure it out. All right, so this would be my intermediate. Why? My intermediate in an SN1 reaction is the carbocation, because that would be the result of the end of the first reaction. So the answer that makes the most sense would be C. The reason we're going to take out B and D as possible options is because those intermediate states only exist in SN2 primary reactions, where one halogen kicks out, or when one nucleophile kicks out the other nucleophile immediately, and there is no carbocation. And X is right when the reaction's about to happen, but it is not the established carbocation. So I wanted to make sure to do a pretty good review before we went on. So now we're going to go over elimination reactions. So like I had went over in the initial objective, an elimination reaction means we are eliminating a small molecule from 2 carbons that are next to each other. And what you need to know are the essential conditions. And so this gets a little bit tricky. If I have NaOH, AQ, AQ means that I have it in water. And what happens is a nucleophilic substitution. And the reason for this is because in water you can have your Na plus and your OH minus ions separated due to ionization. So therefore you have this strong Nucleophile. And you can do that nucleophilic substitution pretty easily. When you have NaOH in ethanol, so sometimes you'll see it called alcohol, or you'll just see it called ethanol. What happens instead of the regular nucleophilic substitution is an elimination. And so you actually do not need to memorize this mechanism. You just need to know that this is what happens. However, I do have the mechanism included because I understand better with mechanisms because it's important to know what bonds are being formed. So the idea is that in an elimination reaction, the nucleophile hydroxide takes this hydrogen. It already has the 2 electrons there, so it does not take the 2 electrons from this bond. So these 2 electrons collapse and make a double bond. But at that moment, when you have a double bond here, this carbon would have 1, 2, 3, 4, 5 bonds, and that is not okay because of the octet rule. So immediately the bromine, which is the weakest link, leaves. It has the lowest bond energy, it has the greatest difference in electronegativity, it is the largest atom, and it would be the group to leave. The halogen would be the group to leave. And so this is how you get this end result. So it is nice to know the mechanism, but you do not need to memorize it. All right, so if I want to favor elimination reactions instead of substitution reactions, there's a couple of things you need to note. Besides the fact that elimination reactions happen in alcohol instead of water, it also should be pointed out that elimination reactions have a higher activation energy. It is the less favored reaction to happen in comparison to nucleophilic substitution. So in order to force an elimination reaction to happen, you would want a higher temperature. So if you run the reaction at a higher temperature and under a hot plate or a Bunsen burner, you are more likely to favor the elimination reaction instead of the substitution reaction. Chemists might want to do this because once you've created a double bond, you can do a plethora of addition reactions. You could add water, you could add any halogen you want. So if you're trying to turn one molecule into another, having an alkene is an excellent place to start. So pharmacists would care a lot about this because in pharmacy, you're always trying to turn one functional group into another functional group because even just changing one functional group changes the whole entire ability of that molecule. All right, so number 2. Elimination is favored with tertiary bromoalkenes. And that idea is that tertiary molecules are more stable, so it's more likely to favor double bonds. Finally, because there is a greater spreading out of charge in the transition state than either SN1 or SN2 reactions, the elimination reactions are favored by ethanol instead of water. All right, so let's take a look. Cambridge question, substitution or elimination? A reaction occurs when a sample of 1-chloropropane is heated under reflux with sodium hydroxide dissolved in ethanol. Which row is correct? See if you can pick up the answer. All right, so ethanol is your key here. Alcohol favors elimination, so we know to take these two out. I have 1-chloropropane, so if I write it out, this is what I have. And no, you don't have to write it out every time, but it's nice to have a visual. This is 1-chloropropane. So I really have one choice, because we know this chlorine is leaving. It has to take a hydrogen from a neighboring carbon, not the same one, because it has to be able to create a double bond between the two carbons. So it's going to take this hydrogen. Those two groups are going to leave, and you're going to have a double bond. So what's the name of that? You got it. It's propene. right. This question is a little bit more difficult. You have to put together something. Dehydration is actually a type of elimination. So dehydration, if we know the basic term dehydration, we know dehydration, if I'm dehydrated, I'm lacking in water. So dehydration means the removal of water, or H and OH. So remember, when I'm eliminating, I'm always removing a small molecule. But there's more. So not only do we need to remove the small molecule, we need to end up with a molar mass of 70 at the end. So you'll need your periodic table handy. See if you can get the answer, and then I will go over the answer. All right, let's see if you got it. So for the first one, think of it like this. I'm removing the OH, and I'm removing a hydrogen. So then that means that I have a hydrogen here, a hydrogen here, a hydrogen here. This hydrogen is the one that's gone, because this is now a double bond. And then I have a hydrogen here, a hydrogen here, a hydrogen here, there, 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 and there. So I have a total of 1, 2, 3, 4, 5 carbons, C5. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, H10. C, 5 times 12 is 60. And H is 10 times 1 is 10, which adds up to 70. But this is not the answer. And the reason why it's not the answer is because it asks which compound is a secondary alcohol. So we want to take this option out. Let's take a look at another. Let's try this one. 1, 2, 3, 4, 5. Same amount of carbons. So we know that it should probably work out. We take this away. We take either one of the hydrogens on either side away. I'll just take this one, take that one away, and then you count the others. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C5H10. Well, we've already calculated the molar mass for C5H10 from A, and we know that it is in fact 70. And we do know that this is a secondary alcohol. So, B is the answer. Why not C? Why not D? Well, C only has 4 carbons, so we know that its molar mass is going to be at least 12 less, because every carbon has an atomic mass of 12. And for D, we have 1, 2, 3, 4, 5. So we do have that C5, but when we take away the OH and we take away the H, we would have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And so the molar mass would not be the same, it would only be 68, which is why the answer, in fact, here is B. So this would be an example of a harder paper 1 type question. All right, so let's take a look at the uses of halogen alkanes. And this will go relatively quick on, but just so you're aware, halogen alkanes usually the halogens notated with X have the following primary uses. They're used in anesthesia. They're used in flame retardants because they're pretty unreactive. That's why they would be used to retard flames. They're used in PVC pipes, polyvinyl chloride. Do be aware that PVC has to be disposed with care. When you incinerate it, which means you throw it in a fire, you can produce HCl gas or tetrachlorodioxins, which are highly poisonous molecules. And finally, they are also used for the nonstick lining of pans. So molecules like Teflon, CF bonds are extremely strong. They have high bond energies, which means that they can be used at high temperatures without breaking down, which is why they are used for the nonstick lining of plants. All right, so which statement does not correctly describe the use of the polymer PVC? If you need to rewatch, you can, and I went ahead and included the structure of the molecule here for you. All right, so which of these was not correct? Not a correct statement. We know that combustion of PVC does make a highly acidic gas, HCl. PVC molecules, be careful with this because the monomer would be unsaturated, but PVC itself is definitely saturated because everything here is single bonds. The empirical formula is the same between the monomer and the polymer, that's true. The monomer is this. That is the same ratio of carbons, hydrogens, and chlorines, so the formulas would be the same, the empirical formulas anyways. And so the repeat unit for this, CHCl, CHCl, is this the same as that? Nope, so the answer is D. Chlorofluorocarbons. So depletion of the ozone layer happened primarily because of the introduction of chlorofluorocarbons in the early 1900s. So scientists made these molecules in a lab, and they started to use them as aerosol propellants, as solvents, as refrigerants, and for many other uses in America. And what we ended up doing is we ended up starting to deplete the ozone layer. And chlorofluorocarbons were banned about 30 years ago, a little bit over 30 years ago, and now our ozone layer is actually being repleted slowly but surely. And so they had caused a very harmful consequence to the environment, and so you do need to know a little bit of why. First of all, chlorofluorocarbons look like this molecule right here. And so the problem is when these molecules, because they are gaseous, when they get into the atmosphere, the sun will actually cause a homolytic fission between the carbon-chlorine bond. Instead of the carbon-fluorine bond, because the carbon-chlorine bond energy is lower, so this actually causes a homolytic fission, and so you end up with a free radical. And so you end up with free radical chlorine, which attacks anything that it can versus free radical substitution, and it reacts with ozone in a sequence of chain reactions. It turns out that one free radical from a chlorofluorocarbon that's produced can destroy up to 1 million ozone particles. So that's why it's been banned for use. That's why you don't really see them anymore. So chlorofluoroalkanes have been used as the refrigerators, but they're no longer used. But they have to be taken care of when disposing of refrigerators. Which statement about chlorofluoroalkanes is correct, or which series of statements is correct? This is the final question for today. All right, let's see if you got it right. Carbon-chlorine bonds, yes, they would undergo homolytic fission easier than CF bonds because the bond energy is lower in CCl versus CF. Unsure? Double check your data booklet. Remember that I did post the data booklet on Google Classroom, so you'll want to have a copy of that handy with you. Or take a picture of the data values for the bond energies and then write them down if you left your books at the school. Number 2, care is taken in the disposal of old refrigerators because of possible ozone depletion. Yeah. In the original sentence, it says care has to be taken. And then yes, because the CFCs can cause the possible ozone depletion. final statement, C2H4ClF is more volatile than C2H6. So remember, volatile means how easily the substance evaporates. So when we're looking for how easily or how readily the substance evaporates, we're looking at intermolecular forces. And when we look at intermolecular forces, the molecule that would evaporate easier would be the molecule that has the lower intermolecular force, the lower force of attraction. So if I compare the molecule here with the molecule there, some of you might have already picked up right away, hey, this is van der Waals, it's nonpolar, which means little to no attraction. Whereas with the chlorine-fluorine here, that means this is polar, which means that it's at minimum dipole-dipole, which means that there is definitely, because of the partial positive, partial negative charge in the molecule, there's definitely stronger attraction. So stronger attraction means less volatile, because less easy to evaporate, because the molecules are more attracted to each other and less likely to turn into the gas phase. So therefore your answer here would be 1 and 2. All right, with that we are done with chapter 16, and we are 2 chapters done from the whole set of material. Have a great day. See you online soon.